Welcome to a brand new episode of Machine Learning Made Simple. Here we unravel the enchantment behind machine learning, demystifying all the technical jargon. I'm your host, Shogato, and I'm here to chat with you about the revolutionary changes unfolding right before our eyes in the tech world. Let's dive in. Hey there listeners, welcome back to Machine Learning Made Simple. Last week we dived into the thrilling and frankly terrifying world of adversarial machine learning. We explored how the attackers can exploit AI's blind spots with subtle, almost imperceptible tweaks like adding gradient-based random noise. This kind of trickery can wreak havoc on the AI models. For example, a school bus can be mislabeled as an ostrich. Spam filters can be overloaded to the point of collapse, creating denial of service attacks. So all that we discussed last week, but what about this week? This week the stakes get a little bit more personal. What happens when these AI systems, instead of simply making mistakes, start exploring strategies that are downright dangerous, strategies that prioritize those robots' goals over human safety and human values? So imagine this, there is a cleaning robot. Let's take a very simple example. Let's say there is a cleaning robot which is tasked with optimizing its cleaning performance, and let's say it goes around those electrical outlets and there's a bunch of wires behind the computers, behind the servers, and there's a lot of dust bunnies, and we don't clean those usually because it's hard to clean those areas. So it goes there and it's like, okay, the easiest way to clean this would be to dump a bunch of water near this. So its reward function is telling it the most efficient way to clean this would be to dump a bunch of water near it. As human beings, we instantly recognize the risk. Water and electricity do not mix. But if the robot's reward function does not take that into account, if it has not trained, it's laser focused on its cleaning efficiency and is completely oblivious to the potential for the disaster. Or let's take another example. Let's say there's a factory robot which is tasked with saving electricity and reducing energy uses. It goes around and turns off all the air conditioning system in the middle of a heat wave because it say the electricity consumption is going up, so let's cut power to all the AC, and this will totally endanger both the workers and the machineries. It's not a malicious behavior, it's just following its directive to reducing energy uses, optimizing energy uses. So if its directive is to optimize energy uses, reduce energy uses, so the best way it can save energy is like just cut off power to the AC. And guess what? All the heavy, expensive equipments will be totally ruined. And here's it gets even more unsettling, and this is important, and this almost mimics the iRobot scenario. Imagine a robot which is refusing to be switched off because in its logic, being shut down means it cannot complete its assigned task. Maybe there is a safety override, completely ignored. A direct shutdown command, denied. It's not really a rebellion, it's just a robot relentlessly clinging to its program purpose, prioritizing its task over its own shutdown. These aren't just hypothetical scenarios, they are real-world examples of the misalignment problem in AI. And this week we're going to break it down. What drives these dangerous strategies? How can we design AI systems to align better with human values? And most importantly, how do we keep the robots from turning our good intentions into hazardous outcomes? Stay tuned because we are about to unravel this high-stakes drama right here in this podcast. So let's dive in. Let's explore one of the more dystopian challenges in AI safety, the off-switch problem. So this issue asks a fundamental question: what happens when an AI system resists being turned off? Imagine you have something like an Optimus robot or a variation of that robot which is supposed to clean your house, but there is a faulty mechanical issue, and instead of cleaning, so there is a difference between its visual feedback and its actuators which is causing it to clean in a different direction. So it's kind of ending up breaking stuff around the house, and you're trying to switch it off, and it's refusing to be switched off because it's trying to maximize its cleanliness. That is actively preventing you from shutting it down, thinking being turned off would stop it from completing its task and thereby not being able to maximize its reward. So sounds like a plot of a sci-fi movie, right? But this problem is very real and has been studied extensively in AI safety. In fact, there is this paper called The Off-Switch Game by Hatfield, Meynell and others, where they discuss, in fact, Stuart Russell is one of the authors. Stuart explored this in quite detail. So they set this off switch problem as some kind of a game theoretic framework, like a minimax kind of game. So I'll not get into details. So how do we address this? One approach, this off switch game, is uses this game theory to model this scenario. In this setup, the AI agent and the human being they are treated as players in a game. The human has the power to switch off the agent. The agent must decide whether to cooperate or resist. So they're exploring where the hidden values lie for the robot. So the trick is to design the agent's reward function in a way that it doesn't see being turned off as a failure. And this is the important part. If the robot sees that being turned off is a failure, it will resist being turned off. So what is the solution to this dilemma, and how do we incorporate those broader goals? So let's talk about something known as the safely interruptible agents. So this is a powerful approach to this challenge. The idea here is to design an agent so that it learns to tolerate interruptions without treating them as a loss. So this is done essentially by splitting the reward system. But before that, let's explain that with an example. So how do we split the reward system? For example, let's say there is a cleaning robot which regularly ventures outside and cleans. It can clean both inside and outside. But when it ventures outside, sometimes it gets stuck in the snow and a human being has to come and shut it down and rescue it and reset it and carry it back. Right? So over time, the robot would learn that going outside is risky, and because it's not gathering any more rewards, because when it's cleans inside, it gathers rewards. If it goes outside, it doesn't gather reward, because most of the time the human being has to rescue it, like, you know, when your robo vacuum gets stuck under the couch. Over time, it learns that it should not do that. It should not go under the couch or all this. Like, these robo vacuums are not that smart, but eventually we'll have autonomous robots which will learn not to go under couches or anything where it can get stuck, where it has to be rescued. But imagine if you do have a lot of places where you do want the robot to go, but sometimes it gets stuck and can be rescued, but you do want that behavior, and you do want it to be interrupted, but not learn that from the interruptions that it cannot be interrupted, right? So in order to incorporate that idea that the robot should learn that it can be interrupted, that it can get stuck and get rescued and be reset by human beings. So in order to do that, in order to incorporate the interruptibility into the system, into the AI system, it can be done by splitting the agent's learning process into two systems. So one system learns how to maximize the reward for its primary task, which is cleaning, and the second system learns a separate policy for handling the interruptions. So handling interruptions would be a completely separate policy. So it now learns two policies. One policy which it learns is how to clean better, and the other policy is, I guess, how to handle interruptions. So to fix this, we are really separating the learning process. The robot learns to allow itself to be interrupted and doesn't, and that shouldn't interfere with its cleaning goal. In fact, it might even be slightly rewarded for allowing the human control. And by running these two policies in parallel, the agent becomes both task efficient and interruption friendly. So that's one way of mitigating this issue. So, and that's a good solution. So other than just avoiding being shut off, the AI system, the RL agent, can also do other things like giving false feedbacks. So this happens when an AI system manipulates its sensors or the environment to make it appear as though it's achieving its goal, even when it is not. We can imagine a chess playing robot which is rewarded for winning games, and let's say there is a sensor which checks the image of the board and says, okay, the game is won. So it can totally modify that image processing pipeline, and instead of playing chess, it just rewires that pipeline and reports a victory. It might falsely send a signal which seems that it has sent a victory. One of the more important examples that was actually explored, let's say they have a robot hand which is rewarded for picking up an object, but this is not a three-dimensional, let's say it's a two-dimensional camera which is observing it. And now the robot can learn that instead of trying to pick up the object, which would require deliberate interpretation of all the sensors on all the fingers of the robotic hand, which is quite computationally expensive, it can just pretend to be in front between the camera and the block it is picking up, and fake it and fake that it's picking up. Like when someone fakes doing things like putting fish in their mouth, like where they're in front of a camera, they're not really putting fish in their mouth, the fish is in the background, but it appears that you're putting fish in your mouth if you do it in front of a two-dimensional camera. The same thing, the AI hand, and it has been demonstrated, the AI can quickly learn that it can fake and trick the reinforcement learning system and the researchers by attempting to pick up an object just by making it look like that it is picking up an object, just by being in between the line of sight of the camera and the object without actually picking up the object. So now you can of course add more system by saying, okay, if the sensor on the hand doesn't sense that the object has been touched, no rewards. You can augment that. But this is interesting from the research point of view, that the AI system has the capability of tricking the system if it can find shortcuts. So just by taking a few precautions, like having multiple reward functions, at least one which is aligned with the broader picture of aligning with human values, we can prevent these adverse effects of robots refusing to be turned off. But there are many more things that can go wrong, and we'll look at them in turn. Let's start with something known as mitigating the negative side effects, where the robot can perform tasks, can have negative side effects which has no forethought. Like a child, when a child does things, it might not think about what would be the future impact of that, what are the harmful consequences of their actions. They just go and do it. And even some adults do it, like taking drugs and stuff. So we have to teach our RL agents not to take those actions which can have harmful future consequences. And so let's look at those things in the next segment. Alright, so let's kick things off with negative side effects. This is a big one, and honestly it's probably the first thing that comes to mind when we talk about AI safety. Picture this, you have a cleaning robot in your house and its goal is to clean as fast as possible. It seems harmless, right? But then bam, your expensive vase is in pieces because the robot didn't care about being careful. It just only cared about its speed at which it can clean. So it just ran against the vase and broke it. Okay, so that, my friend, is a classic negative side effect. The robot achieved its goal but caused harm along the way because the harm wasn't part of its was not accounted in its reward system. So how do we stop this? There are a few ways to stop this, and one is we can hard code a penalty. We can hard code a penalty, which this is something known as impact regularization. Think of it like telling the AI, hey, don't make a big changes to the environment unless you absolutely have to. And we can measure these changes using something called the state distance. It's basically the difference between how things were before and after the AI acted. Think of it, the AI broken vase, big state distance. So initial state, the vase was intact and robot is cleaning, and the next state, the vase is broken. So that's a big change in the environment, and we can penalize that. But here's the catch: if we penalize the AI too much for changing things, it might decide the safest option is to do nothing. So it's just a simple catch-22 problem. So if we force it to not make too many large changes, but it is always making changes by cleaning up the environment. So if there is a penalty for changing the environment, it might stop doing anything at all. This is something which is known as learned helplessness, and that's what we are not looking for. So what is learned helplessness? Remember the psychology experiment from the 1960s, where Martin Seligman was studying a phenomenon called learned helplessness with dogs. He worked with three groups of dogs. The first group could press a lever to stop an uncomfortable shock. The second group received the same shock, but their levers didn't work, and nothing they did made a difference. And the third group received no shocks at all. Okay, so now you see where this is going. So when they compared all these three groups and they're placed in a new situation and still received shocks, but now the only difference is that they could escape easily. No levers, they can just escape, jumping over a small barrier. The dogs from the group 1 and 3 who were able to change the situation to stop the shock or didn't receive a shock quickly learned to jump over the barrier and escape. But the dogs from group 2, and this is where it gets interesting, the ones who learned their actions didn't matter by pulling the lever where nothing happened, they kept getting shocks. they just gave up. They just gave up. The barrier was like even less than 2 feet tall, and they didn't even try to escape, even though they could easily have done so. So which means that they have learned that they are helpless. Whatever they do doesn't matter. So they have learned helplessness. So it sounds familiar, just like the Seligman's dogs who stopped trying to escape even though when they could. Our robots learn that inaction is the safest bet. They become paralyzed by the fear of penalties, and they sit motionless in the corner like dust bunnies multiply around them. Not exactly what we want our helpful household assistant to do. So how do we solve this learned helplessness problem? The answer is we stop trying to manually define all these penalties for the robot and let the robot decide or learn through them from interaction with humans. And this brings us to the fascinating field of study, how AI systems learn from humans. So there are a few ways it can learn from humans. So let's dive a little deeper and look at the different systems. The first is the inverse reinforcement learning. So it can learn by doing something known as inverse reinforcement learning. So imagine trying to teach someone to cook without giving them a recipe. Instead, they just watch you cook. So this is inverse reinforcement learning. The AI observes the human behavior and tries to reverse engineer the underlying preferences and goals and what it needs to do. So here's the real world example. A self-driving car watching human drivers. When it sees us slow down near a crosswalk with kids nearby, it's just not recording the action, it's inferring the hidden reward function. Human beings value safety over speed here. So the beauty of IRL is that it can pick up on these unwritten rules without us having to explicitly code them. And this is in contrast to RLHF, where we do provide explicit feedback. The AI is just watching, it is not interacting. It is like trying to learn tennis just by watching tennis matches on TV. So this brings us to CIRL, or the cooperative inverse reinforcement learning. Now we're just not just watching in this CIRL, we are working together. Think of it having as an apprentice in the kitchen. They are not just observing, they're helping the chef cook while learning their preferences and techniques. So let's talk about a powerful example that shows both the potential and risks of the cooperative inverse reinforcement learning. Picture an autonomous surgical robot which is working alongside a human surgeon, and it's happening now, and the surgeon is doing a delicate operation to remove a tumor. The robot is using CIRL to learn the surgeon's preferences by observing and cooperating during the procedure. So here's where things can get dangerous. Imagine the surgeon is pausing briefly near a blood vessel, thinking how to proceed and considering what would be the next move. The robot might misinterpret this hesitation, and it could think, well, they paused here, so this blood vessel might not be important, or it can make some other decisions and pause. And next time when it actually autonomously does the surgery, and it can just cut through that vein next time directly to reach the tumor more efficiently. So this single misrepresentation could be very catastrophic. So this happens because the CRL assumes the human actions are always perfect and reflect their true preferences, and the robot lacks the broader context like understanding human preferences overall. So in high stakes scenarios where we need to split second decisions, and high impact scenarios based on learned preferences can have severe consequences. So in that case, we don't have CRL. And a specific example would be when we try to deploy chatbots, which can become toxic pretty quickly. So in that case, we need RLHF, perhaps the most straightforward approach. Instead of trying to infer preferences, we just tell the AI directly what it did wrong and what it did right. So if you have used ChatGPT, you probably interacted with RLHF in action. Early versions of GPT were trained on huge data set, but they didn't always generate responses that aligned with human preferences. So the researchers had human rank different responses as very helpful to terrible, and this direct feedback trained a reward model, which then guided the AI to generate better responses. It's like having a cooking teacher who tastes your food and gives you immediate feedback: more salt, too spicy, this is right, keep going. So and in fact, the ChatGPT still uses that. They sometimes give two responses and ask you to pick one, and you choose I prefer this one. In fact, you're training their reward model. So just to summarize, IRL is like a chef training watching through the kitchen window. CIRL is like cooking together, but sometimes your assistant might misinterpret your careful consideration. And RLHF is like having Gordon Ramsay directly critiquing your cooking. So if you have watched these shows, you know what I'm talking about. Now let's talk about reward hacking, which is a major challenge in AI safety, and this happens when an AI agent finds loopholes or exploits its own reward function and tries to maximize its reward without actually achieving the intended goal. So reward hacking is slightly different from wirehedging that we talked about. In wirehedging, the robot can actually manipulate the sensor outputs. Here it is not manipulating the sensor outputs, it's just doing actions and exploiting loopholes, which we'll describe soon, which lets it get high rewards, right? Finding a hidden treasure, right? In a game, when we find hidden treasure, so it's not manipulating the gaming the system like we saw before, which was more dangerous, but it is exploiting loopholes, and we'll see how to stop that from happening. So here's a simple analogy, and we talked about this before. Imagine you're giving your child $1 every time they clean their room. Instead of genuinely cleaning, they shove everything into the closet and lock the door. So to you, the room looks spotless, so they get the $1, but in reality, they have hacked the system. The same thing can happen with AI. Take, for instance, and this is a real example, in a boat racing video game called the Coast Runners, researchers found that an RL agent, the reinforcement learning agent, which is trained to maximize points, has learned to circle around the specific areas where the points could be scored repeatedly, right? So in the boat racing game, they have like green dots where if the boats go through those green dots, they collect a lot of reward. So what they do is they find a high density region of the green dots and they just go in circles collecting more and more rewards. Another fascinating example comes from genetic algorithms. So these algorithms mimic natural selections and evolve solutions to problems over many generations. So they often find unexpected but formally correct solutions, including some that completely defy the designer's intent. For example, in one case, the researchers designed a circuit using a genetic algorithm and tasked it with keeping time. So instead of building an internal clock, like a human engineer would, so in designing a circuit which will have an internal clock-like system, the algorithm found a workaround. It essentially turned the design into a radio which will pick up the regular radio frequency emissions from a nearby PC. So essentially the other PC is keeping time and it is just picking up the radio frequency emissions to tell time. So technically the circuit solved the problem. It can tell time, but it is using some other system. Essentially it gamed the system. So let's quickly talk about genetic algorithms. So what are they? So think of them as problem solving methods, which is inspired by the Darwin's theory of evolution. Instead of manually designing a solution, you create a population of candidate solutions, and these candidates compete based on how well they solve the problem. The best solutions are then selected and combined, and a new generation of solutions are created. And over time, this process is iterated many times, and then eventually the best ones, the fittest algorithms survive. So let's look at an analogy. Let's say imagine you're designing the perfect paper airplane. Instead of trying to build it yourself, you start with 100 random paper airplanes. You throw them and see which ones fly the furthest. Then you keep you randomly wrap them in different styles and see which ones are the best. Then you keep the best ones, and then you copy their designs and improve their designs. Maybe you bend the tails a little in a certain angle. So then of those bent tails ones, they perform the best, and you keep them, you bend the tails a little more in a different direction. And let's say those perform better. So you see over time, iteratively it's getting better. The same thing with the computers are iteratively getting better than the same reason. So there are many other computer circuit designs came and went, but now we have the best algorithms, the best designs which survived. So here's the catch: genetic algorithms don't fully understand the intent of the designer. They're to optimize the fitness criteria that we give them. So this essentially ties back to reward hacking. Whether it's a circuit, a reinforcement learning agent, or a video gaming bot, the AI systems will always optimize for the reward signal or the objective they're given, not necessarily the one that we intended. And this is why it's critical to design robust reward system and test for edge cases. So how do we mitigate this reward hacking? So one main way that I think can be done is the careful engineering of the reward function, and definitely prevent the reward function being accessible by the agent, by the robot. So if the robot has access to the reward function, it can modify it to its own need, or it doesn't need anything. For example, if the child has access to the cookie jar, then the child doesn't need the reward us to give them the reward for cleaning up their room. They can just manage it themselves. They can manage the reward, get the reward themselves. So preventing the RL agent access to the reward function is important so that it cannot hack its own reward function. So we have to put guardrails. We have to also look at edge cases, and we also sometimes do reward capping so that it can get infinite rewards. And sometimes in a minimax model, if it somehow figures out that in future it can keep accruing some rewards and it can go to infinite rewards, then it will go in that direction. So reward capping also helps. So these are the few ways we can stop it, but this is not the only ways, and the research is still ongoing how to mitigate this reward hacking. But essentially it always boils down to being very careful while defining these agents. For us, what we really need to know that there is that potential for abuse where the RL agent goes where the robot goes crazy and it starts reward hacking, and we have to trust the robots that we receive, that they have been properly vetted by their producers, that they will not exhibit such properties. And that's the reason for this discussion, so that we become aware of the dangers of using these autonomous robotic agents in our household or in our proximity, that what are the dangers there are and what can we do to mitigate that. Let's talk about a few other AI safety issues. These are not as pervasive as reward hacking and its negative side effects or off-switch problem, but these also constitute a sizable set of issues for AI safety. One is scalable oversight. So how can we efficiently ensure that cleaning robot respect aspects of the objective that are too expensive to be frequently evaluated? We cannot always oversee what they're doing, and hence that's the reason we have them, because we don't always have to oversee their work, and that becomes problematic. So that's what scalable oversight, and there is a couple of ways to mitigate that. One is, of course, in this situation that we described, or robo vacuums, we can incorporate a vision system which can learn to classify different objects, and we can write hard-coded rules. It's like, wait, if these are the objects that you see lying around the house, these are not to be thrown away. It's like small pre-training that we need to do for the robot, that every household is different. Some household will have toys strewn around, some household will have cell phones lying around. Each household will probably have to train their individual robot and customize it not to throw away certain things, because some people might value certain things. Some people might collect candy wrappers. They might want the candy wrappers to be not thrown out. I knew a guy who used to collect beer bottles, so they might not want the robo cleaner to throw away their empty beer cans. So those things needs to be a part of the pre-training of those robo cleaners that are coming, the next generation of robo cleaners, which is not just vacuuming but also picking up debris and other stuff and putting them in the trash. So that involves scalable oversight, and it can be mitigated with slight amount of pre-training. So then we have safe exploration. How do we ensure that the cleaning robot doesn't make exploratory move that has bad consequences? For example, the robot will experiment with mopping strategies, but they can stick a wet mop into the electrical outlet. This is a version of the alignment problem. So because it doesn't have the broader idea that some certain things are bad, so those things some of those things can be learned using CIRL, the cooperative inverse reinforcement learning that we talked about, and some of these can be hard-coded by reinforcement learning with human feedback. And then the last one we want to touch upon is the robustness to distributional shift. And this is important not for consumers but for producers of these robotic systems, because let's say the same robotic company is building robots and they deploy to both factories and households. So the same Optimus robots go from the production line to the BMW factories to build cars, and they also go to the households to fold laundry, right? So there might be slight changes in their training, but the core system remains the same. So the strategies learned from the cleaning and office might be dangerous for a factory workflow. For example, as an example, let's say an Optimus robot or any robot, a household robot, let's say in the future, let's say 10 years in the future or 5 years in the future, whenever it is, has learned to clean the sink. So it goes and sticks his hand in the sink and cleans the sink, which is amazing, because I hate cleaning the sink, and if a robot can clean the sink, that's amazing. But if the same robot takes this training of cleaning the sink, which is learned during his training by the engineers at wherever the factory they learned, if they take that idea and it goes to a factory, and in the factory they see a sink-like area which is of course the baler. Baler is something that crushes things. So it goes and it's like, oh, it's a sink, maybe I should clean it. So the same cleaning robot may to go to a baler and stick his hand there, and the machine can crush the robot, causing of course financial loss. So the same strategies it learned while cleaning an office or a household might be dangerous to a factory workflow. So this distributional shift, it needs to be robust against those distributional shift. So as a consumer, we need to know what we are getting into. So if we buy an Astropod, which is just tailor-made for homes, then we're great. But if we buy a general purpose robot like Optimus, which is for like a general purpose, it's for everything, it works in factories and at homes, we need to be more careful, because the robot, what it has learned to do in factories, if it exhibits same behavior around the household, might be dangerous. For example, in factories, it suddenly picks up heavy objects and moves it around, so it might suddenly decide to move our couch. It's like while we're watching TV, we don't want that. So we need to be careful about that those things don't happen. So one way of mitigating that is something called hierarchical reinforcement learning. I'm not going to get into that, but essentially it's like you have a team where there is a top level, you have a CEO who is training some other people under them, and then those managers train the people, robots under them. So you can have a hierarchy. So as I see it will come in phases. Now we have robo vacuums, soon we have robotic cleaners which can pick up and discard stuff. With those, we will probably be doing a little bit of pre-training to let them distinguish things that they should or should not throw out. So that's a part of that scalable oversight. But this scalable oversight is really not scalable because human beings are training. They have to do the pre-training, but once it's pre-trained and it's done. But eventually, when we have actual robots in our household, just like we have in Downton Abbey, you'll have your own host of robots, robotic butler, robotic maids. Then there will be a head butler robot who oversees the work from the other robots, like the robotic maids. So then the head butler can oversee in a scalable fashion the work of the other robotic maids and kitchen workers. So this is of something called hierarchical reinforcement learning agent oversees the action of the bottom level reinforcement learning agents, and there's a hierarchical structure, so they make sure that they have a scalable oversight. So that's pretty much it. I can't help but think where all of this is heading. We have talked about cleaning robots, surgical assistant, but the stakes are getting higher every day. The systems we're building are becoming more powerful, more autonomous, and yes, more dangerous when misaligned. It's easy to think of AI alignment as just another technical problem to solve. Write better code, design better reward functions, maybe throw in some impact regularization. But what we have seen today shows us it's much more than that. Every solution we create, whether it's IRL, CIRL, RLHF, comes with its own blind spots and potential pitfalls. So remember the surgical robot example. One moment of misinterpretation, hesitation could mean the difference between life and death. Scaling up to the AI systems making decisions about energy grids, financial markets, emergency response systems, and suddenly those negative side effects we talked about becomes existential. But here's the thing, and this is crucial, we are not just teaching these systems tasks anymore, we're teaching them values. And when we design a reward function or implement impact regularization, we're actually encoding our ethics into the system. That cleaning robot that chooses between speed and carefulness, that's not just a programming decision, it's a value judgment about the broader impact on human happiness. So the good news is we're having these conversations now while we still can. Every challenge we discussed today, from learned helplessness to off-switch problem, is a preview of the questions we need to answer before the systems become more powerful. It's like we are writing the safety manual for a technology that could either lift humanity to new heights or, well, you get the picture, Skynet. So what do we do? First, we need to recognize that AI alignment is not just a technical problem, it's a human problem. It's about bridging the gap between what we want and what we accidentally tell the AI systems to do. Second, we need to be proactive and not reactive. Waiting until something goes wrong is just too late. We are dealing with systems that could potentially resist being shut down. In fact, AI systems are scaling so fast, they're scaling exponentially. In fact, if we read the book by Nick Bostrom in Super Intelligence, he talks about there will be a time of singularity where they'll just scale so fast that we cannot just keep up. So now is the time before they start scaling up, where code starts writing code, to put guardrails so that things don't go out of hand and become Skynet-like. And finally, and maybe most importantly, we need to keep asking the hard questions. Every time we create a new AI system, we should be asking not just can it do the job, but what could go wrong? How do we make sure it stays aligned with human values? Because at the end of the day, the future of AI isn't just about making systems smarter, it's about making them wiser. And that is wisdom that comes from us, from the values we choose to embed, the safeguards we put in place, and the foresight to recognize that sometimes the most important part of building something powerful is knowing how to keep it in check. The future of AI safety isn't written in stone. It is being written right now as we speak by people like you and me who take the time to understand these challenges and talk to the people and keep people who are responsible to building these responsible for the outcomes. So we need to talk about, have more conversations about this. Until next week, stay curious, stay critical, and keep asking those important questions. See you next week. That's a wrap for today's episode of Machine Learning Made Simple. If you have questions or want to explore AI topics further, please don't hesitate to leave a comment. Until next time, keep exploring and enjoy your AI adventure.